Ready.
Our next speaker, Sinai Robins, is speaking on the covariogram and Siegel's formula. Please.
Thanks a lot, Mel. And again, thanks for organizing it. If it wasn't for Mel, none of us would be sharing our research here today. So thanks, Mel. Let's see. So this is the 20th already annual workshop. And this is joint work with Michel Valeiros Martins, who is my PhD student at USP, University of Sao Paulo. This is his picture. I always like to put pictures now of my students and collaborators. And let's see, part one, I'll spend only 5 minutes per part, but I wanted to organize things. Siegel's formula and the geometry of numbers, Carl Ludwig Siegel, as we all know. Maybe less known is the following formula. For geometry of numbers, you're given a convex body P, you're given a full rank lattice L, and the hypothesis is if the only lattice point of L in the interior of this Minkowski difference body is the origin, then we have this formula of Siegel. So the two parts on the left, namely the 2 to the d times the determinant of the lattice and the volume of the convex object, those are familiar from Minkowski's first theorem. The less familiar object perhaps is the Fourier transform, infinite sum over the Fourier transforms of the object. We'll talk about that, but Siegel came up with this early on, 85 years ago, I guess. And then, so Siegel's proof used the Parseval identity from Fourier analysis. Here we'll use a new variation of Poisson summation, which is a little bit more flexible, I find, and it gives you a little bit more juice. But basically, it's kind of the philosophy of Siegel. So this is part one. The difference body, by the way, that's invoked here is in the bottom B minus B. It's the Minkowski difference of any, let's say, compact set B, X minus Y, where both X and Y are in B. It's called a Minkowski difference body. So this is the theorem of Siegel. And there's an interesting quote by Castles, which I'll put in a slide in a second. If P is also essentially symmetric, then it's an elementary fact that the difference body 1/2 P minus 1/2 P equals P. And then you have a simplified version of the statement, but it still looks basically the same. In his classic book of Geometry of Numbers, Castles writes, Siegel is given a stronger form of the Blichfeld inequality, which is also well known, which has, however, remained rather sterile of applications. I like this kind of subdued British humor sometimes. It's kind of funny. Anyway, here we aim to rectify the situation, if possible. A body, by the way, is always defined as any compact subset of Euclidean space. Okay. Part two, the covariogram and the cross-covariogram. The covariogram is defined by the volume of K intersect K plus X. So given any compact set K, move it away by a vector X and look at the intersection. If you measure those intersections over all X, then that's the function. It's called a covariogram. And it's defined for any X, any bounded set K, in fact. It's also known as the autocorrelation of the indicator function of K. It goes by many names, set covariance for probability theorists. And an elementary fact is that you can realize that it's a convolution of the indicator function of K with the indicator function of minus K. So this is an elementary exercise, but all of these things are simple so far. The cross-covariogram, as you can imagine, you can do it not just for K, but any two bodies, K and L, and then that measures how kind of they're related to each other. And there are many conjectures about these functions. Until a week ago, I didn't realize that Bombieri had one of the main theorems that we had, so I thought it was ours. It turns out it was Bombieri's. About 7 to 10 days ago, we discovered this. Luckily, we've managed to extend Bombieri's results, so I'll talk about extension, but it was very recent. Anyway, Bombieri, 1962, extended Siegel's result, and his extension is the following. We had exactly the same statement, but with a different proof. But in any case, clever guy, this Bombieri. So Enrico Bombieri did this when he was 22. Amazing. So this covariogram on the left-hand side of this extension of Siegel is what we talked about, the volume of Q intersect Q plus X. And it's this lattice sum on the left is the periodized version. Just think of it as a periodized covariogram. You periodize over some lattice L. Given this periodized version, it lives on the torus and therefore has a Fourier series. You expand the Fourier series, that's the right-hand side. The Fourier coefficients are the convolution of these two indicator functions, which turns out to be the norm squared of the Fourier transform of the body. And so this is the extension. Turns out not to be so hard to prove, but Bombieri, yeah. And then there's a conjecture of Matheron, 1986. This is more recent. That, I apologize for the airplane above. The covariogram uniquely determines every convex body K. Among all convex bodies, of course, up to translations and reflections, it uniquely determines the body. It's known for essentially symmetric convex bodies. It's known, it's not hard to prove, in fact. Bianchi, and was worked on for many, many years, Bianchi and Averkov proved that it's true in dimension 2, that the covariogram of K uniquely determines the convex body K. In 2009, Bianchi has shown that the covariogram uniquely determines all three-dimensional polytopes. And then there's current research on this uniqueness, how uniquely the covariogram determines a body. It has to do with well, it goes by many conjectures. This conjecture of Matheron, Georges Matheron from 1986, who wrote a book about this as well. In any case, just to set notation quickly, this is the Fourier transform we'll use. We put the minus 2 pi I in the exponent. In case f is the indicator function of the body, of course, the Fourier transform of the body just means, by definition, you apply it to the indicator function. So the Fourier transform of the body is just by definition the integral over the body of the complex exponential. And by the way, a lot of the stuff that I talk about and various connections are in a new book that I've been writing, A Gentle Introduction to Fourier Analysis and Polytopes, which will appear in the AMS, the Student Mathematical Library series. It'll be about 400 pages all in all, but anyway, you can see more connections and a lot of the proofs also in there. And of course, so yeah, I said it goes by many names. Sometimes it goes by the name of the phase retrieval problem in Fourier analysis. If you know the norm squared of the transform, can you retrieve the phase? In other words, can you retrieve the whole Fourier transform, and therefore, because the Fourier transform is a complete invariant, retrieve the whole object. So Fourier methods are natural here. Let me show you a new variation of the Poisson summation formula that we found, which we found to be useful in this context, and an extension that we found of Bombieri's theorem. Then I wouldn't be surprised if all of a sudden next week I'll find that Bombieri proved this new variation of Poisson summation when he was 10 years old, but let's see. So here is the variation of Poisson summation. Suppose you have a function g that's completely supported and continuous, and such that both g and its transform are in L1, in other words, absolutely integrable. Then you have this usual statement of the Poisson summation formula. But the hypotheses are always different. If you go to literature, there are over 30 different variations of Poisson summation, always giving some different sufficient conditions for the following statement for this equality. And usually the equality is pointwise at the end. And usually it's both sides are uniformly convergent and continuous functions of x and so on. And so here the same conclusion holds here, but the hypothesis is yet a new hypothesis as far as we know. All the different hypotheses are slightly different kinds of spaces depending on the application. In any case, given any convex set, compact set K, if the Poisson summation holds, for this convolution, we'll say that K is admissible and the function is admissible. So we'll focus on these convolutions, which are the covariograms. And that's what, well, it wasn't exactly what Siegel did, but it was what Bombieri did, in fact. So it's very natural to wonder, by the way, how general the class of such admissible sets can be, because they arise naturally in the study of covariograms and the cross covariograms, where you have two different bodies. So our extension, in fact, is for the cross covariogram, where you allow more flexibility. We allow two different sets, just bounded sets, A and B, let's say. given any two functions f and g that are in the L1 space intersect the L2 space, in other words, both absolutely integrable and square integrable, if they enjoy the following two properties, let's see what the two properties are. Both functions are bounded, and f is compactly supported on A, and g is compactly supported on B, for instance, indicator functions. Then for any full rank lattice, we have the following formula. Well, the convolution first is admissible. In other words, we have to prove that Poisson summation holds for the convolution of any two L2 functions. It turns out it does. So, and then the formula below is our extension of Bombieri. And this extension is very useful because the extra flexibility when you allow B to be different than A all of a sudden opens a new world of possibilities. So the formula, the extension of Bombieri is below. I highlighted it. The cross covariogram is this volume, and then you periodize it over the lattice, and the periodization has the spectral formula on the right of the bottom. When I say spectral, I just mean an infinite sum of something involving transforms. Okay, part 5. So we're going quickly because we only have 25 minutes. Consequences and applications. Our new application of both Bombieri and the extension of Bombieri is to K-tilings. You know, it's translating Euclidean space by translations of a fixed convex body, let's say. It doesn't have to be even convex, but you have some compact set and you want to translate it by some lattice and determine whether the set of all translates by a lattice is a tiling of Euclidean space. Given this definition, this is the definition of K-tiling by translations with the lattice L. Given this definition, when K equals 1, of course, it's the classical definition. When K is greater than 1, it's the multi-tilings, which is the new thing. And I should note that the field has kind of exploded in the last 5 to 10 years, where there are weird, new, and exciting connections between K-tilings and frames. In Fourier analysis, K-tilings and some combinatorics, K-tilings and the Fougletti conjecture, K-tilings, and for us, Poisson summation in Fourier analysis. And the first person that I know of who did some beautiful work on this is Mihalis Kolountzakis. So Mihalis realized early on some of these early connections to Fourier analysis, and later we all built on Mihalis's work, I think. And in any case, it's still kind of moving forward rapidly, this field of multi-tiling. And today we'll give yet a new equivalent condition using Fourier transforms for multi-tiling. So this is one of our applications of Bombieri and the extension of Bombieri. So just to show pictures are always fun. Given a non-convex polygon Q on the left, you see this green polygon. The difference body Q minus Q is on the right, the bluish one. It's always kind of a little bit different and bigger. And if you look at the integer points inside, those are the integer points we use in order to determine whether Q multi-tiles the space or not, in this case with integer lattice. So when you move around the Q with the integer lattice, you get these funny looking nice pictures. And the first corollary is, given, let's say, an admissible set, for example, a compact set Q, let L be a full rank lattice, then we have the following inequality. So these periodized covariograms over lattice, in fact, are finite sums because Q is bounded by definition there. So therefore, it's a finite sum. Obviously, if you move Q plus Q sufficiently away from itself by some translate by a lattice point N, then of course, it's going to be empty after a while. So we have another slight extension of Bombieri. And if you look at the index of the sum, it turns out you have to sum only over the interior points in the difference body. Bombieri didn't have that. It requires a technical lemma, it turns out, that's not trivial to show that the sum can be restricted to the interior lattice points of the difference body. In any case, this lower bound is also new. And the interesting thing is when equality occurs, and it turns out when equality occurs in this universal lower bound, it turns out that it is exactly when Q tiles or multi-tiles the space. So the equality below occurs if and only if the original compact set Q multi-tiles the space with a lattice L. So far, so good. I can pause for questions. Okay. I hope I'm not going too fast, but anyway, it's all going to be online, recorded. But so yeah, so this is the first application of Bombieri, this lower bound and the equality case, completely understanding the equality case in terms of the multi-tiling bodies is I felt was kind of interesting and nice. Going back to this example that we had before, using this corollary 1, we can check that Q satisfies the equality case, and therefore this Q does multi-tile. It's not completely obvious that it multi-tile. It's also not difficult, but one can illustrate it. One can illustrate corollary 1, the application, by brute force using these green integer points in the interior of Q minus Q on the right. In any case, corollary 2. Here's a weird spectral formula, a new spectral formula for the volume of a compact set. So let Q be admissible means that the indicator function can be used in the convolution of the indicator function with itself essentially can be used in Poisson summation. But for example, any compact Q is admissible. And let L be any full rank lattice with the property, now we need a special, so if you pick a lattice L with the property that Q is disjoint from all of its non-zero translations by vectors from L, and in addition, Q plus X is also disjoint from its non-zero translations by vectors from L. This is easy to construct, by the way. Then we have the following weird kind of formula for the volume of any bounded set, measurable set. The volume squared has the spectral formulation on the right. This is new. I don't know what to make of it yet, except that it probably is of theoretical interest more than practical interest. In other words, if you want to theoretically compare the volumes of various objects without actually computing them, then it may be of interest, I think, but one never knows. So this is a new spectral formula for volumes that we get from as another application of Bombieri's result, and there's a variation of this which I didn't have time to write for the product of volumes of two objects, which is a consequence of our extension of Bombieri. By the way, as examples, it's easy to evaluate the Riemann zeta function at positive even integers by looking at specific polygons or simplices in dimension D and computing both sides of these corollaries. And we do that in a paper on the archive. Some questions for further research. And I don't know if I have time to go into this, but I guess maybe I should, maybe I should stop here. Thank you. I went too fast, I think.
No, that's great. Thank you, Sinai. Do we have any questions for our speaker?
Yes, I have a question. Do you see any connections between your generalizations of the Poisson summation formula and the veil representation?
I don't know. Honestly, I don't know, Carlos. By the way, good to see you again, Carlos. I don't know if you have something in mind. I encourage you to pursue it. I really love this new direction of research. But I don't know, honestly.
All right. Okay. All right. Thanks.
Okay. Hi, Sinai. So this is Lee.
Hey, hi, Lee. How are you?
Yeah, good to see you. Yeah.
Good to see you.
Right. So yeah, I have a question. So in the last slide, right, you're talking about the theta values, like at even integers, right?
Yes. Yes.
So since you are talking about this kind of polytopes or cones, can you use this to do something about the multiple theta values? Like a double theta value?
Oh, like the Zagier type zeta values?
Right. Yeah.
Well, to be honest, I didn't try. I would guess it depends. I would guess so, but it really depends on the particular zeta values you have in mind, because it comes from, let me show you where it comes from. If you look at Bombieri's result, for example, the extension of Siegel by Bombieri.
Mhm.
Here it is here, yeah. If you look at this, what we do to retrieve these zeta values is we pick some polytope, let's say an integer simplex in dimension D, a very simple integer simplex for which you can compute explicitly the Fourier transform. We compute brute force the left-hand side at some constant, and then we compute the Fourier transform, the norm squared. We expand it all out, and we brute force these infinite series. And these infinite series turn out to be these multiple zeta values, because the Fourier transform is basically a constant over the product of linear forms. It's a finite linear combination, and the fact that it's a finite linear combination of a constant over a product of linear forms, that you recognize an infinite sum of those is kind of a Zagier type, zeta value, but it depends. Yeah. It depends on which linear forms you get from the geometry of your polytope. You know what I mean?
Okay. So yeah. So looks like there may be some high dimensional analogs, right?
Yes. I think you can get some, but I'm not sure all. But I think you can get some of these zeta values. Yeah. Sure.
Okay. Yeah. Okay. Very interesting. Thank you.
Great. Good to see you again, Lee.
Yeah. Good to see you.
Other questions for our speaker?
Yes, and I've got a quick question. First of all, good talk. Good to see you as always.
Good to see you. I can't hear you.
For a student. Oh, good.
Okay, now I can hear you.
Oh, lovely. Good talk. Good to see you as always. I was curious, do you know if there are any, if anyone has tried to a vector space over finite fields or something like that? Or, I mean, I know certain analogies would fall through, like interior, but I wonder if some of this could be done maybe for student research or something. Or if you know if somebody's already farmed it out, or.
Let's see if I think part of your question was kind of swallowed by the internet, maybe. But did you say that? Did you ask if some of this can be done over vector fields, over finite fields, or in particular Poisson summation, or?
Oh, I mean, yeah, obviously Poisson summation, but some of with these bigger sets. Do you know if anyone has done this over finite fields, or?
I don't think it has. It's an interesting direction. I guess the thing to do would to go back and to start with the Poisson summation for a finite abelian group, which we all know, and then if you start with those and the induced characters on the right-hand side that you get from the finite Poisson summation formula for finite abelian groups, then maybe you can prove an, and I don't know, that's an interesting question. Maybe you can prove an analog of Siegel or Bombieri for that.
Yeah, I just didn't know if it had been done or if it was obviously trivial, or I'm thinking maybe something for like a student to work on. You know, it seems like someone could read through this and sort of translate. So.
Yeah, I don't know if it was done. It seems like it should be possible, certainly, right? So it seems like it's one of those things. Yeah, if it was not done, it's kind of surprising, right?
Yeah.
So I don't know. Yeah, I haven't seen it. So
okay. Well, maybe I'll send you an email about it at some point.
Sure.
Good to see you.
I think it's an interesting question. Most things that have to do with Poisson summation formula over finite fields or over finite abelian groups end up being relations between generalizations of Gaussian sums. So it would be interesting to see if one just simply try to write some of the results of Sinai in terms of for finite fields, what kind of Gauss sum relations arise. I think that is an interesting question. I had not seen it before, but it may be possible to formulate some things. Yeah.
Yeah, and by the way, if any of you guys want to pursue this, I would. Anything is you should go ahead and pursue it. I also agree that it's Stephen had a very nice question here, which I have to admit I didn't pursue. I was always because I'm always thinking about the Euclidean case version recently and trying to do it for compact sets or bounded set in Euclidean space. But it's a very natural thing you're asking, Stephen. And let me see. Yeah, offhand, I haven't seen it. I don't know. It's surprising. Yeah, it's surprising that it hasn't been done, right? If it hasn't been done, yeah. Very nice. Very nice. Okay.
Other questions for our speaker? If not, Sinai, thank you again.
Thank you.